I have the pleasure of presenting the final presentation in this section. This is a topic actually we've been thinking about for quite some time, maybe up to 10 years or so, and really is a problem that we've only just cracked. So I'm excited to show you what we've been thinking about and keen for any feedback that you might have. This is in particular addressing agent-based simulations, where there's this long-standing problem where you go to compare two simulations, and a lot of what you see in that comparison is just noise. And so it's hard to pull out the real signal. And so we think we have an approach using this idea called common random numbers that I'll tell you about today. There we go. So this is all about comparing simulations, which is something we do all the time, for example, in a scenario analysis. So let's just start with a simple scenario analysis. For example, we want to assess how many deaths might be averted by a vaccine. So what we and everybody else would do is run a bunch of simulations without a vaccine, then run a bunch of simulations with a vaccine, and then just do some basic math to figure out the difference. What's the expected value of the difference and the standard error of the difference? And there's this nice n, the number of simulations on the bottom there. So if we run enough simulations, eventually we can get confident in the difference here. This is great, but we might pause and just ask ourselves, what's causing the differences? Well, there's a couple things. Of course, there's the mechanistic effect of the vaccine. That's the main reason that there's fewer deaths. But there's other things going on here. For example, you can see that these are different populations. And in fact, the simulations are different even before the vaccine is introduced, right? And I'll argue there's a lot of additional unwanted noise even after we introduce the vaccine that's kind of clouding our vision here. So can we do better? Of course we can. One idea is to use common random seeds. And that comes from this covariance term. If we can induce a positive covariance between X, the base simulations in red, and Y, the vaccine simulations in blue, then in fact, it would look like this. Everything's now identical up to the introduction of the vaccine.